Chapter 7, Data Analysis and Probability. Before we get into this, I want to look at one quick thing here, and that is a circle graph. Sometimes you'll see it called a pie chart, something like this. And you know that any circle that you have, if you were to start right from the middle here and begin right there like that, a circle is exactly 360 degrees all the way around. Okay? So this is 90, this is 180, this is 270, and this is 360. So all of it all together of a circle, there are 360 degrees. Half of the circle would be 180, and so on. When you're working out probability, and you want to find out, let's say you have 10 shots, and let's say you got 2 of your shots, let's say you were shooting at balloons at a carnival, and 2 of them were hit the red balloons. So 2 out of your 10 shots hit the red. Well, if I take 2 out of 10 and change that to a decimal, 2 divided by 10 will be 0.2. Of course, to change that to a percent, just times it by 100, and you would end up with 20% if you wanted to work out percent. But if you wanted to know what is 2 out of 10 as a circle graph, you'd simply take your decimal and times it by how many degrees you have in a circle, which is 360. So if I were to take 0.2 and times it by 360, so 0.2 times 360, and my answer is 72 degrees. So 2 out of 10 is 72 degrees. So if I wanted to draw the red, how much was red, I'd simply take my protractor, and with my protractor I would have to measure out 72 degrees. There we go. So let's move him on over here. Measure out 72 degrees and put a tick right where 72 is. So 60, 70, 71, 72 is about right there. Oops, a little less. Right there. So I'll move him out of the way. And now I've just drawn 72 degrees, because there's my mark. So this here would be the red. Now if I want to figure out, let's say it was 3 out of 10 was blue. So I should shade in my red right here, just to kind of so you remember. So 3 out of 10, let's change that to a decimal. So 3 divided by 10, 0.3. Times that by 360 degrees, and the answer is 108 degrees. So taking my protractor again, what I'm going to do is move it, and of course rotate it, if I can, to make sure it starts off right on the 0, right there. So I need 108 degrees for blue. So there's 0. You got to start where your last angle ended. And I go all the way over to 108 degrees is about right there. I'll move him out of the way, make my line. So 108 degrees would be about right there. So this right here is 108 degrees, and it was blue. So you'd keep going. Obviously, there's only 5 shots left that you haven't taken. Okay, so I would say 108 degrees should be probably actually right about there, if I measured it right. Okay. And there should be 5 out of 10 shots left, or half of it still not done. And of course, half of a circle is 180. So you need to remember that. If you don't remember that section, you need to go back to the previous unit that dealt with making a circle and determining how much a circle actually is when you change your data to a decimal. Okay, so back to data analysis and probability. There's lots of different things. Some people call it chance. There's lots of different ways to look at it. Sometimes you can roll a die. So this is one die, two dice. If I roll this, there's 6 possible outcomes, or 6 possible things it could get. So what's the chance of getting a 2 out of that? Well, it's 1 chance out of 6 possible outcomes. Looking at this guy right here, a spinner is another favorite one to use. There is 8 actual sections on this spinner, so 8 numbers. What's the chance of getting an even number, which is the white? There's 1, 2, 3, 4. There's 4 chances out of 8 possible outcomes. Okay, so data analysis is all about chances or probability to get a certain outcome. All right, so when you look at certain graphs, though, that represent certain data, we'll start off looking at 5, I guess, if you look at the double bar graph, different types. This one right here is a circle graph, okay? And it's really good at showing parts of a whole. So if you have maybe 10 shots and you want to see which one has the most out of the whole thing, a circle graph is really good. It shows parts of the whole. You can show percents pretty easily on this, and you can compare different sectors real easy. Some of the things it's not so good for, sometimes it's kind of hard to draw. They're not very easy to draw sometimes, because you got to do a little bit of calculations first. And sometimes you don't see the total. You kind of got to add up all the different amounts. So if this was 50, and this was 20 or something like that, and this was 5, you'd have to add them all up, instead of just being able to see sometimes what the total number is real quick. This one over here is a bar graph. Okay? This is so easy to compare the different values, and it's got a scale which makes it really easy to calculate. You just go right across and see. And it's pretty easy to draw. It's one of the easiest ones to draw. The only down thing to this is sometimes you can fool around with the side here, the scale, and it can be misleading, as we'll find out in the next section. So it doesn't also show the percent of them. It's a little harder to compare them and see what the percent is as a whole. Okay? Whereas the circle graph's a little bit easier to compare the parts of the whole. This one here is a line graph, and a line graph is pretty easy to draw, and a line graph is best to show how data changes over time. So you can really see whether it's going up or whether it's going down. This one here is not my bank account, because this one is going up here. So it's pretty easy to see that, and you can also kind of estimate where it's going to next. So in this one, you can kind of say, yeah, it's probably going to keep going a little bit up. So you can do an estimate sometimes. The only downside to this one, sometimes it doesn't go nice and neat like this. Sometimes the data can go like this, and it's, it's not always going up and down. It might be going zigzag. And it doesn't show the parts of a whole. It doesn't show you what each one is compared to the next, or compared to the whole thing. This one over here is called a pictograph. Picto meaning picture, and graph meaning, making a graph. In this one, you have to use a picture that represents a certain amount. And in this case, an apple here really represents 10 apples. So every full apple like this means 10. This one here, half an apple, is 5. And of course, if you wanted to say, I don't know, a quarter of an apple, it would be 2.5. So you can really change it up like that. So on this one here, this says 1, 2, 3 apples, but really that's 10, 20, 30. This one is 10, 20, and 5 more, so it's 25. And the benefits of this one is it really easily compares different sets of data. It looks nice, it really looks graphically appealing, and it's pretty easy to find the total of something when we're doing it. The only downside to this one is that sometimes the symbols can make it hard to read if you've got a whole lot of them. In this case, we don't have a whole lot because we had 10 apples to be one of these. If it was only 2, we'd have to have a lot more apples to represent 30. We'd have to have 15 apples. That's going to take some time to count up. and it doesn't show the parts of a whole and can be difficult to draw because you want to try to get all the apples the same, because you could really fool with somebody's eye if you make your apples really big. So this could be 1, 2 apples, and yet it looks like the same as the 3 apples if you make them bigger. The double bar graph down here is kind of like the bar graph up here, except we're comparing 2 different sets of data. Okay, for example, in this one, you got test scores here. So it shows fractions test with and without preparation. And of course, without preparation is this guy. With preparation is this guy. So it really compares 2 different sets of data pretty easily. And it's pretty easy to draw. The only thing is, on this one, you can only draw it with discrete data. That means you have to have actual data in here to put into it, and it has to be something that's measurable, and it can be difficult to read depending on the scales, and sometimes confusing. You really got to look at what's up here and what's down here, and then take some time to interpret what this really means. So that's the different types of graphs you might see. Okay, so there's the circle graph. Okay, again, it's good for showing parts compared to the whole thing. Then you've got the bar graph and, of course, the line graph. And then our lovely looking pictograph is there. So that takes us to section 7.2, misrepresenting graphs. In other words, how can sometimes graphs show stuff in a way that's misleading or isn't really what it looks like? One way to remember it is DA pits. So misleading graphs can be the pits. They're the main letters, D pits. So it's D, P-I-T-S. So if you're looking at any kind of a graph, you're going to look at misleading somebody by doing things that start with D, and then P, and then I, and then T, and then S. Now I'll explain what that means there now in 1 second. Okay, so here's what we have here. We've got a hot dog eating contest here. And if I were to go back, I've got different things here. I've got cake, okay? I've got this one right here, Miss Nasias, Little Big Belly, and Mr. Gonna Eat a Lotta, okay? So I'm going to make my graph here of the hot dog eating contest. And here's what we've got. Dr. Stoma Cake ate 8 hot dogs. So I'm going to show 8 hot dogs for this guy right here, Dr. Stomacake. So where's Dr. Stomacake is right here. So I need 8 hot dogs. So on this scale, it goes up by 2s. So there's 2, 4, 6, 8. Right there. Okay. Now watch what happens when I change my scale here and I start at 2. I'm going to need the same amount, 8, but this time it's not going to look quite so high. So right now this is showing 8. Now if I were to draw the next person, or the next class, Little Big Belly ate half as many as Miss Nasius. So where's Miss Nasius? Miss Nasius ate 2 more than Dr. Stomacake. So if Dr. Stomacake ate 8, Miss Nasius ate 10. So let's go and find Miss Nasius right here. And we need 10. So here's Miss Nasius. 2, 4, 6, 8, 10. Now, representing 10 down here, I already got 2, so that's 4, 6, 8, and 10. Now, Little Big Belly ate half as many as Miss Nasia, so that's 5 for Little Big Belly. So let's see what we got here. That's 2, 4, and of course 5 would only be up to there. And if I were to show 5 for this one right here, that's 4 there, and 5 would be halfway between 4 and 6. And the last one to do, of course, is Mr. Gonna Eat a Lotta ate 2 less than Little Big Belly. So Little Big Belly ate 5, so must have eaten 3. So there's 3 shown right there, because we already got 2. And of course, going over here, that's 2 and 3 would be about right there. All right, now looking at this graphs, it almost looks like Mr. Gonna Eat a Lotta didn't eat hardly any, like ate almost half as much as this person, right? When we know that if we look at this graph here, that's not the case. They ate 3, while this person ate 5. This person ate 3, while this person ate 5, but yet this looks like less than half because we've changed the scale on the side here. Okay? If we change the scale to start at 3, okay, then we could cover that up. And look what would happen if we started at 3. It would look like Mr. Gonna Eat a Lotta wouldn't have eaten any. Okay? So you could change the scale on a lot of graphs to make them look whatever way you want. Okay? So let's look at this one here. What does the D pit stand for? D is for data. Okay? First of all, you got to make sure they're actually using the data that's given. Okay, so sometimes it can be smudged or fudged by not including all of the data, leaving out something. The next one is proportional. Okay, make sure the bars are in the correct proportion for the data given. Make sure they didn't switch the size of their things like that. The interval, okay, and the scale. So make sure they've got the bottom and the side correct. So let's look at this one right here. This one says pizza was 100, so pizza is up to 100. Burgers is 65. As you can see here, that's wrong. They don't even have it done right here. Tacos was 10, and steak was 25. So you got to make sure that the data actually matches. Looking at the bars to see if they're proportional. You've got the number of students, but look how wide they made these bars. By making them wider, like this, it kind of makes it look a little bit different. It makes it look like this one is more important or thicker than the others here. Okay, the I, or the interval, you've got to watch what they're doing down there. You've got Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. And it says, when Mrs. Kimmerlin was training for the San Francisco Marathon, she graphed her weekly running log. Is it in order? Well, let's look at it. In this case, you got Monday. Monday is 7. Tuesday is 5. Wednesday is 0. Thursday is 10. Friday is 6. Saturday is 8. And Sunday is 18. And if you count up the side here, 0, 2, 4, it looks like you're going up by 2s. 0, 2, 4, 6, ooh, this is 7. 10, 12, 18. You notice that they changed the scale up here. They're not even going in order here. So be careful with the scale. This one here, the title, is this graph, the label here, is it misleading? Here's what we have here. 0, 4, 8, 12, 16, and 20. Jojo, Coco, and Dee Dee. Okay, we're not even sure what this here is all about. Okay, we don't know what the title is. Sometimes it's just showing 3 things, but we're not even given what it's comparing it to. And of course, watch that scale. This scale did not start at 0. And for it to be true representation, okay, there should be 5 more down below, so there should be another block down here shaded, and another one here, and another one here, and another one here. So be careful that the scale is not changed. It should start at 0. Okay. So this one here, is this a misleading graph? Well, let's see. What about the scale on the side here? It starts at 10. Absolutely. So for all we know, the number of students who have their texts here or receive from 0 to 4 should be 10. Yeah, it is. It could be representing 10 right there. But it looks like they got none because they only started their graph at 10. Okay. So you got to be careful they don't change the scale, and sometimes they change the bottom here as well. All right, so moving on from graphs as to why they could be wrong representing data to getting some data or independent events. Now, when we're looking at probability and chances, we're looking at a couple of important terms, and that is event and outcome. Okay? An event is what's actually happening. An event is something that you're doing, whereas the outcome is what happens as a result of that event. Okay? For example, if I were to take this event here, my event is flipping a coin. Okay? What is my outcome? Well, let's find out. I could have a head or a tail, and in this case, I got a tail. So the outcome here is a tail. Okay, my event here is rolling a die. And my outcome is getting a 3. That is my outcome. What were my possible outcomes? Well, I could have got a 1, a 2, a 3, a 4, a 5, or a 6. Whereas for the heads or tail, the coin, heads or tails. That's it. That's all I could have gotten. Now, when we're talking about something that doesn't affect each other, if I flip a coin, okay, and then roll a die, okay, it doesn't really matter. One does not affect the other. Okay? I can roll this and flip this all I want, and this one's not going to make me get more heads or tails just because I flip them one right after the other. So I'm going to look at this one. What is my chances of getting a head and a 6? Well, the easiest way to do it is to make a graph. I've only got 2 events. One is flipping a coin, okay? And the other one is rolling a die. Now, what are my 2 possible outcomes that I could get when I flip a coin? I could get a head or a tail. What about when I roll a die? What are my possible outcomes going across the top here? Well, I could get a 1, I could get a 2, a 3, 4, 5, or a 6. So it's kind of like we're matching it up in our multiplication table. So if I flip a coin, I could get a head, and then I roll the die, I could get a 1. I could also get a head and a 2. I could get a head and then a 3. I could get a head and then a 4. I could get a head and then a 5. I could get a head and then a 6. My other possible outcomes, I could have gotten tails first. So I could have gotten a tail and a 1, a tail and a 2, a tail and a 3, a tail and a 4, a tail and a 5, or a tail and a 6. Now, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 possible things I could have gotten. 12 possible outcomes. What's the chances of getting a head and a 6 together? Well, there's a heads and there's 6. There's only 1 chance out of 12 that I could have gotten a head and a 6. Now, if I want to change that head and a 12, head and a 6 to a decimal, I just go 1 divided by 12 equals 0.08. We'll round it off to. So 0.08. To change that to a percent, just times it by 100, which will give you 8% chance of getting a head and a 6. So getting a head and then getting a 6 will not affect each other because they are independent. Here's another one. So we've got 3 possible outcomes for our rolling of, or our spinning of our spinner. And again, there's 6 possible outcomes for our die. So I'm going to make a table, and for my event, I'm going to have, for my spinner, so there's my spinner. What's my 2 possible or 3 possible things? I could get a blue, red, or green. So that's what I've got here. So I'm going to need one for blue, red, and green. Now at the top then, I need to come up with my die. And what's my 6 possible choices? Well, I could get a 1, 2, 3, 4, 5, and that'll give me 6 choices at the top. For the die, oops, I could get a 1, I could get a 2, a 3, a 4, a 5, or a 6. So I put my 3 possible outcomes for my first event and my 6 possible outcomes for my other event. So this works very well when you have just 2 events, 2 things happening in other words. So for my first one, I'll fill in all B's across here. So B, 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 because it's all blue, blue. For here, I will fill in all reds. And for here, all green. Now going down, they will all be ones. 1, 1, 1. And this, of course, will be 2, 3, 4. See, all I did was say the chance of getting a green, that is a 4. And of course, these will be 5. And this will be 6. Like that. So how many total possible outcomes could I have? 3, 6, 9, 12, 15, 18. So there's 18 possible outcomes. So if I want to say what's the probability or the chances of a, let me see, a blue and a 5. Well, let's find the blue and 5. There's 1 chance out of 18. What's the probability I might get a, how about a 6? Well, there's 1, 2, 3 of them that could have come up 6s. One of them's blue, one of them's red, one of them's green. So the chances of getting a 6 would be 3 out of 18. Okay. Which, funny enough, works out to 1 out of 6, which is the same as the die. Okay. So whenever you're given something and you only have 2 events, you can make a table with the outcomes, possible outcomes of one of them down one side, and the possible outcomes across the other side of the other event. Okay, so looking at this one here, this is a pretty famous one where you've got to draw 2 of them, and you're going to see what's the chances of getting a red and then getting a green right afterwards. So we want to see the probability of getting a red. Well, the chances of getting red is 1, 2, 3 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 3 out of 10. And then what's the chances now of getting a green right afterwards if we put the balls back in, of course? We've got 1, 2 out of 10. So we want to get this followed by this. So the probability of red followed by green. And the easiest way to calculate this then is go 3 out of 10 and you multiply that by the chances of getting your green right afterwards. And your answer will be 6 out of 100, which of course if you calculated it as a percent, it would end up being 6% chance of picking a red first, putting it back, and then picking a green. So 6 out of 100.